Cool. Welcome everyone to today's community outreach call. We've got a special presenter today. I'll dive a little bit more into that a little bit later. But as you guys are aware of our antitrust policy notice, if you haven't been through this, you can get it in the hyperledger meeting minutes. We do release this a day after the call, usually along with the recording as well. And then again, also please adhere to the code of conduct. Okay, so today's agenda is just some introductions if we've got any new people on the line. We've got one community update, and then we've got a special presentation today. And then the Q&A. Okay, are there any new people on the line today who would like to introduce themselves? Okay, no one.
I guess I'm new, but I can introduce myself later.
Oh, go for it, go for it. Introduce yourself. Okay. Okay, so in terms of community updates, last week we have applied to Intersect to become a special interest group. We aren't a formalized working group as of yet, but the application has been sent to Intersect, so hopefully within the next week or two, we should have an update to see if our special interest group got accepted. If not, we will be applying again and trying to work with the community over there to see if we can get the SIG going. The SIG will be around, it's focusing specifically around identity, and a little bit more of a focus around Hyperledger Identus, of course. Okay, so today, let's move on to the juicy stuff. We've got Jesus with us. Jesus, if you guys don't know, is part of IOG. Jesus holds a PhD in applied cryptography, MSc and BSc in computer science. And before working at IOG, Jesus worked at IBM Research, BBVA, and the Spanish National Cybersecurity Institute. So he's got quite a long history of research behind him, but today he's going to chat to us a little bit about DidCom. So Jesus, without further ado, I'd like to hand it over to you.
Sure, thank you, Faye, for the introduction. Let me open the webcam. Okay, there you go. So now let's see if I find the window to share. Oh, this does not. I can just share the desktop. Okay. Can you see do you see my screen?
Not yet.
No? Oh, I need to grant permissions to Zoom. Sorry, I didn't use. Oh, it seems I need to get out to draw log off and on again.
Oh, that's perfectly fine.
Yeah.
Using a
Will be a minute. Sorry about this. I don't use Zoom often. Sorry.
the joys of a Mac.
Okay. Let's see if this time works. Okay, now do you see it?
Yes, we can see your screen now.
Okay, that's good. Now what I don't see is if anybody writes or something, so feel free to interrupt me with questions during the talk. So as Fai said, what I'm going to be, so we did some research on DidCom and in the last, actually this has been in the last 2 years more or less, and it finally got published got accepted in CCS, which is a very nice applied cryptography venue. This is joint work with Fabio, Christian, and myself. So that's what I'm going to be introducing today. This is actually a talk that the last time I gave it took me like 40 minutes. So I'm going to be skipping a few things here and there. The idea is to take 15 minutes more or less. So I understand that everybody here knows what are DIDs. Everybody here knows also what is DIDCOM. Otherwise, just interrupt me right now. So what we have done.
We do have someone that's saying they don't know what is the ID, so maybe it would be good to start.
Okay, yeah, sure, no problem. So the IDs are essentially, I like to think about them as a new PKI type. So like X509, but well, you have different data structures and oh, I don't know what I did. You have different data structures and yeah, different processes kind of, but in the end it's like you can think of it as a public key being associated to a name, to a, I don't know, DID colon example colon Alice or something like that. You know that string and you can fetch a public key that's related to that person or machine or whatever. They are a W3C recommendation, so they have been adopted. This is actually what a DID document looks like in the real world. So yeah, they have been they are now a W3C recommendation. So this means that, well, it's quite popular at the moment. And now DIDCOM, if I like to think about it as the equivalent to TLS in the internet, to TLS or SSL, but instead of using X509 certificates, you use DIDs. So if you want to fetch the public key that's associated to Alice, instead of going to a certificate authority, whichever you use usually, you have to resolve it via a DID method, like DID Prism or DID key, DID peer, whatever. So basically, this DIDCOM allows you to establish a secure communication channel between a sender and a recipient or a set of recipients. The thing is that DIDCOM is quite widely used in SSI, but to date, there was no formal analysis. This is not good. If you ask any cryptographer, they will get nervous when they realize this, because even though DIDCOM is based on well-known standards, the fact that it has not been formally analyzed really means that we don't have full assurance of whether the claimed security properties are actually achieved or not. So we knew this, so we decided to look into. We decided to try to unformalize DIDCOM, or parts of it at least. The thing is that DIDCOM is a very wide framework, so we decided to focus on DIDCOM's encryption modes, and precisely we try to answer these three questions: whether they achieve what they informally say they achieve, whether we can do better, and and if we missed something. And well, in the three cases, the answer is affirmative, sort of. Now within DIDCOM, we have two main encryption modes. One is unencrypt. You can see it as a black box, in which you input a message. The sender computes this ephemeral key pair, and the sender has to specify the public keys of the recipients. So Bob1 up to Bob N if he wants to send to N users. And the output of this is some DIDCOM message that's encrypted. With unencrypt, what you achieve, or what DIDCOM claims to achieve, is that this DIDCOM encrypted message is confidential, so no third party can access the contents of the message. It is unauthenticated, meaning that the receiver does not know who the sender is. and it is sender anonymous towards third parties. So if a third party observer is looking at the network, he will not know who sent this message. And outcrypt is essentially the same thing, but it is authenticated, meaning that the receiver of the communication of the DITCOM message knows who the sender is and gets certainty of that this is the real party who is sending the message. But it is not sender anonymous towards third parties. So if there is a third party observing the communication, even if this third party cannot decrypt the message, he will know that Alice is sending some message to Bob. Then there is a third encryption mode that is described in the specification of DITCOM. And this is what we call the naive composition of unencrypted and outcrypt. So basically, you run first outcrypt, you take the output of that, and you run that output. You use that output as an input to unencrypt. The result of this is kind of the best of both worlds. So you get a confidential message. Nobody can read its contents unless it's the recipient. The sender is authenticated towards the recipient, so Bob will know that it is Alice who is sending this this message. But this DITCOM message that is produced as an output, it is sender anonymous towards third-party observers. So some third-party observer who is wiretapping the channel will not know that this is Alice sending a message to Bob. Okay, so very quickly, we found one subtle issue in the composition of unencrypted and outcrypt, and you can think of it as, well, in DITCOM, Alice can send a message to multiple Bobs. Actually, this is usually the case here, is that Alice is sending the same message to multiple devices owned by Bob. So you would expect that the message that each device of Bob receives, they are actually the same. But when composing unencrypt with outcrypt in certain modes in DITCOM, you cannot actually prove that this is the case. And this is because DITCOM supports two encryption modes, two symmetric encryption modes, AES in GCM mode and Chachapoly, which are not committing schemes. This is not a bad case on it, a bad thing on its own, but it can be a bad thing for the way in which unencrypted and outcrypt are composed in DITCOM. The thing is that it's trivial to fix. So DITCOM also supports this symmetric encryption, which is AES with CBC in HMAC mode. So just by using it, you get rid of this problem. So that's it. Other than that, we come up with in our research, in our paper, we come up with a model of DITCOM. Is this image here? I will not go into the details, but this model basically allows us to prove, to prove that DITCOM achieves what they claim to achieve, with the exception that I mentioned before. Then you have to use unencrypt with a committing encryption algorithm, which in the case of DITCOM, this must be AES in CBC mode with HMAC. Okay, so, but we didn't only prove the security of DITCOM's encryption modes, we also looked at the efficiency. So we ran some benchmarks on using the main library in the GitHub repository, the main GitHub repository of DITCOM back then, at least. It's the one provided by SIGPA. And we observed that so here in these graphs, the red line is the cost of encryption with unencrypt, and the blue line here is the cost of encryption with outcrypt. And in the x-axis, you see the number of recipients towards that you are sending the message to. And then you can see that when you are composing unencrypt with outcrypt, you essentially double the costs. The same applies for decryption. And the same applies for the message size, the resulting size, the size of the resulting DITCOM message. So this means that we are kind of duplicating work. So we started thinking of why this happens. And the reason is that essentially you are running two key derivation functions. Again, I will not go into the details for the sake of time. And you are actually encrypting the same metadata twice. So this A, B1, and B2, these are the identifiers of the sender and the recipients. And you include them once without crypt, and you then include them again with unencrypt, at least the recipients. Plus, you include twice these encrypted keys, this string here means encrypted content encryption key. This is a symmetric key that is being used to encrypt the actual data. So you see that you are including it twice. So you're duplicating a lot of things in the message that you introduce, that you compute. Now, this is not really a big problem in terms of time, because if you see in this image here, we are talking about a matter of milliseconds, but it may be a problem in terms of the space, because here, just with a very short DID string, the example.name, we are talking about going from 500 bytes per message to more than 1,500 bytes per message. So you are even more than duplicating. Well, this is not actually duplicating. You are going from 750 to about 1,500. So the message can actually be a problem. So we actually, this is the pseudocode of what unencrypt and outcrypt do, and these gray these instructions highlighted in gray are the differences. So you can see that we are basically doing the same thing twice. So what we did is come up with a way, again, I will not go into the details, but we came up with a way in which we save duplicating a lot of work. So the result is that the message is much shorter. We only include the identifier of the recipients once. We only include the encrypted symmetric keys once, and we only include one ephemeral public key. All that was included twice it's included twice in the original approach. Another thing that we missed is that in all modes, in all encryption modes in DITCOM, the sender identity, sorry, the recipient identity is being leaked to third-party observers. So if Alice is sending a message to Bob, a third-party observer will know that Bob is receiving a message. In unencrypt, a third-party observer will not know that it is Alice who is sending the message, but Bob is always exposed. So we came up with a way in which we can hide the fact that Bob is receiving a message. And the way in which we do it, this diagram explains the full detail, but it's actually very simple. So we take a 1 and encrypt it with a key that only Bob can derive again. And the same for all the recipients. So whenever Bob receives a DITCOM encrypted message, he can, in this way, he can do a trial and error and try to decrypt this flag. And if he gets a 1, then this means that this is a message that was intended for him. If he fails to decrypt or if he receives garbage, then this was not a message that was aimed towards him. This will not be applicable for all cases. So if there is a big set of possible recipients, this will be inefficient, but there may be settings in which this is possible and this is realistic to deploy. So that's the main contribution. So we proved security of DITCOM encryption modes with this caveat that there is some you should use AES in CBC mode. we improve the efficiency of the combined mode, the unencrypt and unencrypt combined mode, and we give this receiver anonymous mode. This is this array anon. So a natural final contribution is to actually propose a mode that gives you all of it. So the receiver anonymous functionality plus the improved efficiency combined mode. And this is what we call array AO. This is a very hard to pronounce name. And that's it. We have, this is the paper. This is the link to the full version of the paper that just got accepted. You have security proofs there, all the definitions. This will be published, the proceedings version, which is a sorted version, will appear in CCS 24. And we also, all the benchmarks that I showed you before, the code is available here. If you don't even want to download the repository, you can, this image should still be available. To be honest, oh no, actually I ran it last week. So it is still available, so you can run the benchmarks in your own machine. And you should get something that looks like the plots that I showed you before. And that's it. I think I made it almost in 15 minutes. Open to questions.
Cool. So we've got one question. John, I know you asked a question about is the amount significant? What was that referring to?
So when he was talking about the doubling of the cost in the overall scheme, is that significant, that doubling of the cost, or is it kind of nominal?
I would say that for the computation time, it is not significant. Meaning that you move from, if I remember correctly, okay, let me go to the graph before. We move from 0.005 seconds, so 5 milliseconds, or even one order of magnitude less, to 1 millisecond of yeah. So here it is. So you go encrypting a DITCOM message towards SIG recipients, let's say, in the worst case. It takes, in our benchmarks, it took less than 2 milliseconds. So, and when running the composed mode in the way that DITCOM allows you to do it now, it will take 4 milliseconds. So this is, in my opinion, this is not a big thing. I mean, the thing here is that the way to optimize it is so simple that it may be worth it. Because also you have to think that in DITCOM, you have to you typically want to concatenate multiple hops. So this overhead happens once per hop, per DITCOM hop. So if you send your message, maybe I want to send a message to Phi, but instead of sending the message directly to Phi, I route it first to David, then to John, and then to somebody else. So this means 3 hops. Per hop, your costs will be doubling. So maybe if you have multiple hops, so many hops, this may end up being representative. If you only have a few, probably not. In my opinion, but the thing is that this is easy to implement. So it may be worth it. The bad thing here is that it is not fully standards compliant. This relies on some RFC draft from the IATF, the implementation of DITCOM, that does not strictly support the changes that we propose. But we believe that it would actually be a very good thing, because this would not only impact DITCOM, but the JSON web encryption set of standards at large. And it's a 2x improvement in computation. But then what is really relevant in the DITCOM case is the size of the message. Again, this 2x improvement is per hop. And here this graph was computed literally using did : example : well, not name, but Alice, I think. And you can see that when you are already sending an encrypted message towards 6 recipients, while unencrypt and outcrypt take you about 1,500 bytes, their composition takes you about 3,500. Now, you have to count this per hop. So if you have 4 hops, this would not be 3,500. This would be 12,000 12,000 or 14,000 bytes. So that's a lot. And in our actually, I don't know why these are some old graphs. I forgot to add them. But our costs are, let me see if I had here. No. I forgot to include this, sorry. But the costs, I mean, they are in the paper and you can get the plots in via the Docker image, but the costs in our improved mode are essentially the same as in the original modes. So you basically don't get this 2x per hop. So that's a big gain, in my opinion. Yeah.
Awesome. Thank you. David.
Yes, this is a great presentation, and we've had the opportunity to talk about this before. I do have a question about key exchange. If Alice and Bob, can you still hear me?
Yeah, I can.
Okay. Zoom says it couldn't, so I apologize. So if Alice and Bob are going to communicate, Bob needs to know Alice's key to authenticate, and it's very specific to Alice. Do you have a proposal for the key exchange?
No, actually, that part we don't touch because I don't have that figure here. What DITCOM does is simply downloads the ID document associated to the recipient, to Bob, and then they run a non-interactive key exchange. So it's a local computation by Alice. There is no message exchanges at that step. That's quite.
Thank you.
I mean, as far as I can see, that's quite efficient. Maybe there are some things that I miss, but yeah.
No,
Happy to discuss it further.
Cool.
Bjorn.
Hi, great presentation. Thank you. So I also dabbled a bit in DITCOM some time ago, took the SIGPA implementation and ported it over to .NET. And what I saw over the last months or over the years that DITCOM didn't really catch on until now, especially like the advanced features, having multiple hops in between, multiple mediators, multiple relays in between. So did that change? So how do you see this? I mean, you modeled this, that we have multiple relays so that a message can have multiple hops. Did you see something like this in the wild somewhere? Someone implemented this, or is this still more theoretical?
Probably, I think I saw Fabio in this call. Probably Fabio can answer that question much better than me. Sorry to put you in the spot, Fabio. So if you want to take that, very good for me. Otherwise, there are other protocols that do actually kind of the same thing. Maybe this helps. So Tor, for instance, they follow this onion approach. Like you have to go to decide a path of. In the case of Tor, they are called routers, not mediators, but they are essentially the same thing. And the costs, of course, are linear in the number of intermediate hops. And in their case, that is quite practical. So maybe in the case of DITCOM, it's just a matter of refining these things. And in the real world, it may have, well, rather than in the real world, in the academic world, which has impact in the real world as well, security-wise, it may have benefits as well. Because you don't, as long as there is one reliable party in that path, then you can already make security proofs work. And that's good, security-wise and privacy-wise. Now, there are inefficiencies like the ones we discussed today, but so for instance, with this improvements that we propose, the most severe ones, the most severe inefficiencies, they go away. At least the ones that we can see. So yeah, I think that's promising. I know if I answered your question, if I deviated too much, Björn, feel free to ask
Thank
again.
you so much. But to continue this question just a little bit, this was more like a formal analysis, but did you look at the possible attack vectors or the mitigations, or especially with multiple hops?
The part of multiple hops, we didn't look at it because the only looking at the encryption part is complicated enough. But the good thing about the approach that we took, so we used what's called in cryptography, it's called a composable framework. This means that once we have proven security of encryption, of DITCOM encryption, we can just assume it works, and we can even compose it with itself, which is exactly what happens when you are when you're building a chain of multiple hops. So you encrypt towards the first hop, then you get the result of that and encrypt it towards the second hop, and so on and so forth until you reach the final destination. So the fact that we used a composable framework makes it very easy for the next step, which is to analyze the security of the route, of the full route of mediators. I can't tell you whether there would be any problem or not, because, well, there are usually a lot of nuances here, but to me it looks good. If there's any problem, shouldn't be hard. Yeah.
Yeah, thank you.
Thank you.
Cool. John had a question about, could you speak a little bit to how the order of hops are determined? And does each message become more secure with each hop, or does it stay more or less the same in terms of security?
So as far as I know, the hops are, again, if somebody knows more about this than me, please correct me if I'm saying something wrong. So there are two parts to it. One is the recipient. The recipient in his or her DIT document, they specify their service endpoint, I think it's called, and on a service endpoint, I think there's another name like routing path or something like that. So long story short, the recipient tells you what route you need to follow in order to reach out to him or her. So this means that the recipient is deciding, in order to talk to me, you have to go through Alice, Bob, and Charlie. And then the sender may do the same. The sender may say, okay, in order to talk to Bob or to this recipient, I have to go through Alice, Bob, and Charlie, but I want my message to be routed first towards, I don't know, I ran out of names, to Fabio, David, and Faye, which are the first names that I see here in the screen. So in the end, this means that the final route will be Fabio, David, Faye, Alice, Bob, Charlie. And the recipient has chosen part of the route, and the sender has chosen part of the route. I think that's the way it works. If somebody knows better, please correct me. And then whether the message becomes more secure with each hop, I would say that it does, but maybe I'm biased here because I'm thinking in terms of the way in which Tor works, which, as I said before, it works in a kind of very similar way by building this route. And in the case of Tor, as long as one node is honest, one node in this path is honest, then you can argue about security. You can say that in the case of Tor, that your message is private, is anonymous. I would say that the same applies here. Privacy-wise, it does not apply security-wise, because if somebody can break the security, I mean confidentiality-wise, because if somebody can break the encryption, maybe that breaks some of the things. Let me see. Okay, maybe that would depend at what step of the chain is the honest node placed. But yeah, I cannot give a definite answer. Looks like it can help in some situations and maybe not in others.
Jesus, I've got two questions. The first one is, what are the, like, in your opinion, what are the biggest challenges DIRCOM faces regarding scalability and adoption?
Probably the best person to answer that either. But so regarding scalability, in my opinion, the worst thing is this, what we saw today, that if you want to get full sort of kind of speaking short and bad, if you want to get full security, like being the sender being anonymous yet authenticated towards the recipient, which this forces you to use the composed mode, this unencrypt and outcrypt composed mode. In that case, you get a message that is twice as big as what it should be. Well, not twice, but the metadata is twice as big as what it should be. And only with one hop. And if you chain 3 hops, then it's 6 times worse. So that's a big problem scalability-wise, especially if you take into account that in some DID methods, the identifier, which is the thing that you are duplicating, can be very long. It can be in the order of several hundreds of bytes, or even kilobytes, maybe, I don't know. So that's a big bottleneck, in my opinion.
Sure. Okay.
Yeah.
Last question, might also be a little bit challenging. But how do you see DIRCOM evolving over the next maybe 5 to 10 years?
I think I don't know. I think they are on a very good track. I mean, they are using reasonably well established standards. The cryptography is sound. We didn't find anything weird. Only this subtle thing, which is really subtle. Even we had to discuss it a lot internally to make certain that we were understanding it. So I think it's good. In my opinion, what's more challenging is to answer things like, why do you use DIDCOM and not TLS?
Okay.
Because there is no definitive answer for that. It simply is better suited to the scenario that DIDs create, in my opinion. Yeah.
Sure. Okay, that makes sense. That's fair enough. We've got another question from John. He's asking, is it likely that DIDCOM will accept the proposed changes as standards?
We have actually reached out to them. Actually, they were very, very helpful in clarifying some doubts regarding how DIDCOM works. I don't know. I hope so. They were open to this, but in some cases, so in the case of the receiver anonymous mode, this is easy to integrate, meaning in the sense that it does not require changes in the RFCs that upon which DIDCOM builds, but the improved combined mode of unencrypted and outcrypt, that one does require changes, minimal changes, but it does require changes. And for them, they told us that it would be actually kind of a requirement that this is these changes are compatible with the standards. Yeah, if it were up to me and we had enough manpower and time, I think that would be very good.
Awesome. David.
I want to come back to what Jesus said about DIDCOM and adoption and what's gonna drive adoption of DIDCOM. I think it's and Jesus, I agree with you on the fact that it is basically built for purpose around the use case of DIDs. Why not just use TLS? I've always wondered why they didn't just use TLS with DIDCOM in the first place myself. So for DIDCOM to really get adoption, my expectation would be that it's going to go hand in hand with SSI as a whole. and that it will add features and capabilities specific to SSI, to the optimization of communication and communicating features that are DID specific. I don't see DIDCOM taking over, for example, WhatsApp or Signal or any other kind of communication protocol, point-to-point encrypted communication protocol by any stretch. I see this as very much built for purpose. So adoption is really going to go, excuse me, hand in hand with SSI, increased feature capabilities.
Okay, I've got a follow-up.
I agree.
Are there any real world, I mean, we spoke now about built for purpose. Are there any real world applications where we can think of that DIDCOM would be built for purpose?
So what I liked we looked, not me, and definitely not only me, well, during this research, I mean, in all academic work, you always try to say, okay, this is super necessary because there are a lot of use cases that are using this. So you have to start looking into what are people using DIDCOM for. And one use case that I liked is the one for distributing anonymous credentials. They are using it, as far as I know, in the British Columbia government, or they were using it while we were doing this research. And that use case I like a lot, and also I like it because it goes very well. It works very well with this new mode that we propose, with this receiver anonymous mode. Because if you want to distribute a credential that is also an anonymous credential, you should expect, I mean, the user who is receiving this credential should expect, or I mean, I would definitely expect that my identity is not being revealed. Not only when I use my credential, but also when I am receiving the credential. And DIDCOM right now does not allow that, because like I said in the presentation, the receiver identity is always leaked. And in our case, we propose in our research, we propose a way to hide the identity of the receiver. So that's a very nice use case for DIDCOM and our research as well.
Perfect. Thank you. Well, thank you, Jesus, for the lovely presentation. Do we have any more questions on the line for Jesus before we close this call? No questions. Okay. Well, Jesus, thank you again for joining us and sharing this presentation with us. It was really insightful and informative. As always, everyone, I will be sending out the meeting minutes along with the recording tomorrow. So if you guys do want to catch up and listen to the recording again, feel free to do so once the meeting minutes come out. And we'll see you next week on our Maintain and Contributor call. Thank you, Jesus, again.
Okay. Thank you for
Cheers,
having me.
everyone.
Have a good day.
You too. Bye.
Bye.